Let me see. So far, how many people have answered? 8 people have answered.
Yeah,
It's not
we
a
are
lot.
13, we are 15, so try to pull to reply also for the remaining people. I posted again just in case went back in the history.
Right. So someone, okay, you sent it again. Yeah, I'm gonna leave this open and then we can revisit that. So Pepe, like as more people keep joining, remind them to answer this poll, please.
Yeah.
Okay. So I'm gonna go ahead and get started. Right. So what's the agenda for today, right? So as you know, I didn't finish the first class, so we're gonna finish the transition from support direct machine for classification and finally start talking about regression, but in a higher level, because apparently people want more to like spend more time like running the code on Jupyter Notebook. So like we're gonna go a little faster there. Then I'm finally going to start with the topic of the second class, which is the introduction of the optimization, right? Usually I would talk about like more regression before moving to loss functions and regularization, but because we lost too much time in the first lecture, I got that part out. So we're going to jump directly for one type of regression, which is the linear regression. And why is that? Because that's going to have more components in common to what the perceptron demands. So like that's going to be an easier transition, okay? We're going to talk about like other types of loss functions. We have seen one so far, which was the hinge loss, right? For the supporter vector machine for classification. And then I'm going to talk a little bit about regularization, which was a topic that already came in the first class, okay? And then finally, we're going to start perceptron. And then I'm going to leave that for like when we get there, okay? So if you remember, right, we discussed about the idea of like support vector machine as being this method that gives us the optimal hyperplane. And why is it optimal? Because you're trying to maximize this margin, right? Which essentially it's defined by these two vectors that I have a message here already. Oh, okay, that's was Pepe. So we have these two vectors that are being supported by as many points from the two classes as possible. And those are the supporting vectors, right? Which basically defines the support vector machine. Very well. So we discussed a little bit about this geometric margin, right? So like how, what these weights that we're training, essentially they stand for like, what's the position of this hyperplane. And this position is defined by this normal vector, which like it's perpendicular to the hyperplane, right? So that's the vector W that we discussed here. And this is the margin as you see, right? And then we discuss about what's the output of this method with respect to like the classification of those points as being the product between the vector that's pointing from the hyperplane to each one of these points for each one of these classes, right? And this product being positive or negative basically tells me what's the end classification for each one of them, right? And the point that I get all the points correctly, we had this loss, right? So if I get all the points correctly, means that the output of my model, which is f of x, and the true label, which is like what's the true value of that point, they're matching. If they're matching, this should be equal to 1. Therefore, the loss is 0. So like that's essentially when I go to a loss 0, which means that I have all the points being classified correctly. Therefore, the method has converged. The model has converged. Like what's the best solution for classifying these points? Okay. Very well. And then we stopped here, right? Which is like, okay, now we have seen how to use support vector machine for classification, which is this idea of finding these hyperplanes that are being supported by these vectors, right? Another message. That's still Pepe. Okay. So, and now we're going to do this migration from like seeing how this applies to classification to regression, okay? And I asked you guys if you had any intuition about how this transition will take place, right? Because here, what we are doing was essentially to use this margin that's given by the supporter vectors, right? To say that I want these points to be outside of this margin, right? So what should change for me to be able to use the same approach, but for regression now? Could you guys comment a little bit on that? What you think we should be doing different in this strategy? So, anyone? someone said last time that like what we want to do is essentially to like, instead of having this margin defining that the points should be outside of it, for regression, we should say that the points should be inside of the margin, right? And that's exactly the rationale, okay? But for that, we need to change a little bit the type of loss function that we have, right? Why is that? So the difference between how we're setting the problem for classification and how we're setting the problem for regression now essentially stands for saying that if I have this margin that's still defined by the epsilon, right? If I have these points inside of this margin, right, inside of these boundaries that are still defined by these supporter vectors, right? I say that these points are within the margin, therefore the regressor is doing its job, right? So essentially it tells me like how much of tolerance I have, right, for the regressor, right? Such that, for example, if you see that the difference between what's the true value of the point, right? So like that would be like the y-axis here, and what's my estimate of the position of that point are within the boundaries of this margin, which here are defined by this epsilon, right? This should be an epsilon. I messed up with this symbol here. The loss is zero, right? So like if it's inside the margin, the loss is zero. If it's outside the margin, then it's actually the product. So like that's the difference that I have between the position of this point, right? And how far away it is from like where it's supposed to be. Okay, if it's inside the margin, doesn't matter what's the difference between y and the output of the model, which is f of x, right? It's zero. Otherwise, it's the actual value of that, right? So since we're going to talk about the application directly, I think maybe it's easier to just go to an example, right? Very well. So like for this quick example here, just for the sake of illustration, let's think of this problem, okay? So here, what we're trying to do is essentially try to find a regressive model that's going to take as inputs the number of rooms that I have for a house and try to estimate what's the price that I should be paying for that house. And that's like a data set that's quite standard called the house price in Boston, right? So as you can imagine, Boston is an expensive city. So the more rooms that I have, right, more I'm going to be paying for it, okay? Of course, you have like some outliers, as any type of data usually has, right? So what you observe here is that if you simply train this method with like epsilon that says that's like I'm willing to have as a little bit of margin for error up to $5,000, right? So that's the epsilon that you see here. I'm going to end up with a regressor that looks like this, okay? And why is the case? Because I'm trying to fit a model that definitely is going to have a bunch of outliers, right? And I'm telling this method that like try to get as many points as you can within this margin, right? But this margin right now is quite narrow, right? And that implies that like in order for me to maximize as many points inside the margin as I can, I'm going to have to sacrifice the precision for the outliers. You see? So like a method that's like this is kind of like too stiff, we would say, is not capable of like generalizing for new points, okay? And what's the strategy here is essentially to try to add some flexibility to it by incorporating how much deviation from the margin you're willing to accept, right? And that tells you like how much you're willing to take these points outside of the margin. So if you have this deviation from the margin being higher, right, which here is going to be conditioned by a constant C, the higher the margin that I'm willing to have, right, more flexibility I add to the model, right? Because now those I'm considering as acceptable mistakes, okay? So if you make the model too stiff in the sense that like I don't want any mistakes, so like try to minimize this margin as much as you can, right? I end up with a model that's like gonna be performing poorly for like outliers, right? If I want to try to include as many outliers as I can, I need to add more flexibility to the method. Therefore, that's the role of the C. So like how much I'm willing to go above the margin, how much of deviation I'm willing to accept, right? Very well. Some people refer to this C as the slack variable. So like you're going to see people like referring to that with different terms, but essentially it stands for the same thing, which is like how much flexibility I'm willing to have in order to incorporate more points within these margins. Okay, So for example, in this example, if I set this C to be equal to 1, right? So by default, it would be 0 in the previous case. Now I have a highest margin. So like, again, what the C is doing for me is essentially saying like how much I'm willing to let this model incorporate or move around this hyperplane, which is defined by the blue line here in this 2D case, right? How much I'm willing to move this thing and still have mistakes. So greatest the C, more flexibility I have in this hyperplane that I'm fitting, okay? As you can imagine, now I have two parameters that we call the free parameters of this problem, right? Which now stands for like the margin that I'm defining. So this margin here is this $5,000 margin, right? So you can roughly see here, right? Like by the magnitude of the placement here, that this margin corresponds roughly to 5,000 in the upper direction and 5,000 in the lower direction, right? And the C stands for like how many points I'm willing to consider outside of the margin is to consider it a good fit, right? So those are two parameters that I have flexibility to play with, and they're not being optimized by the process of like refining the weights, right? All that the method is doing, the supported vector regression is doing, is to play around with the position of the hyperplane, right? Which is the red line. Now, what's this margin, the epsilon that we're defining, and what's the deviation that I'm willing to accept? Those are free parameters, which like you're gonna define yourself, right? Very well. But since it's something that we're going to be defining ourselves, right? Probably you can imagine that there is also a way for us to optimize these parameters, right? So like, which is not intrinsic to the way how the optimization supported vector regression works, right? Because supported vector regression, again, is just optimizing the placement of the hyperplane, but you can refine what's the C. And like one of the ways how you can potentially do that, right, is perhaps by running like some grid search, right? So in this quick example that we have here, for example, you see that I'm changing this C, right? So like we have played with like C equal to 0 in the first iteration, then we move to C equal to 1, and then you can keep increasing the C. And again, by increasing the C, I hope you remember that I'm saying that I'm willing to make greater mistakes with respect to like having more outliers, okay? And I'm fixing the epsilon. So like the epsilon, so these margins here, they're still set to be like 5,000, okay? So what you observe is that the greatest, the more flexible you make the method by increasing the C and therefore like the deviation margin, right? You see that the number of points that you get within the boundaries, they tend to increase as well, right? Which is essentially what we want. Because if these points are inside the boundary, if you remember the loss, right? If the points are inside the boundaries, we say that the error is 0, because that's the boundary that basically defines to me like that I have a good approximation of the data, right? So like you see that the loss is not uniquely saying how much I'm deviating from the hyperplane, but how many points I get within the margin, right? I don't know how many of you know how linear regression works. But like, as we're going to see in a little bit, the linear regression takes uniquely the distance that I have between the hyperplane, right, and the placement of the point. So like, even if this point is close enough for supported vector regression, the error is 0, even though it's not exactly on the hyperplane, on the line, right? For linear regression, this still has an error greater than 0. Right? And those are a few of the differences that I'm going to be highlighting as we move like to linear regression and then finally perceptron, right? Is like, what are the assumptions that these methods make? Okay, very well. And I hope you can appreciate that now that we have this C that's optimized for having as many points as possible within this margin, right? Which is like the number of points that I have within these black lines. I get like a fit that looks better overall. So like with 6.3, that's how it looks like. For 1, it was a little bit more tilted, and for 0, it was even worse. Okay, very well. Now, some cons, right? I have been talking about all the benefits of using supported vector machine for regression, right? which is this degree of flexibility that you get, like how much error we are willing to take. But there are like some cons with respect to the use of supported vector machine for regression. And therefore, that's why it's not as popular as perhaps using like actual machine learning neuronal networks for running regression, right? So some of them, so like the fit time complex for supported vector regression is more than quadratic. So like you have an issue with respect to how many points you can actually run with it, right? So this usually becomes a problem when you have very, very large data, which usually is the case because like we live in the big data era, right? Like we have a lot of data about everything nowadays, right? So like they don't scale very well when you have like millions of samples, right? In fact, when you have like more than 10,000 samples, people already start suggesting that you don't use SVR, but rather like its variations, right? So like SVR, like supported vector regression, the way how it's implemented on the main library, which is like sklearn, and we're going to see a little bit about that now in the tutorial, right? You have several types of kernels that you can use, right? And which basically stands for like, what's the type of transformation that you do to the data, right? Everything that I have described to you so far, it's the linear supported vector regression, right? Which is like one specific type. And you have this approximation that's already like implemented for optimal. It's an optimal implementation just for linear supported vector regression, okay? Or this other one that's like SGD regressor that I'm not gonna get into it for the sake of time, okay? It underperforms in case where the number of features for each data point exceeds the number of training samples, right? So if you have, should I discuss that? Maybe not now, yeah. But the main point is that like it also underperforms when you have too much noise, right? So for example, one of the things that we discussed before is that this is trying to find the best boundaries for separating the data, right? Which implies that you have a degree of separation between the data, like for at least for this case, right? If this data is overlapping more, right, you have like noisy data sets, it's much harder to find such supported vectors, right? And what usually is going to happen is that these hyperplanes is going to be moving around and just not converging. So you're going to end up with a method that simply doesn't converge anywhere. So that's also problematic, right? And for cases like that, then you have to start thinking of a method that doesn't necessarily consider that the correct approximation is finding such boundaries that can separate the data, but just as good as it can, right? So like no optimal hyperplane, but rather any hyperplane that minimizes a metric. Okay, good so far? So one last point about this, right? Let me see how I'm doing time. Okay, yeah, we're doing good so far. So like one last point about this. So I have been talking a lot about these linear spaces, right? So like examples like these data sets, they could be separated by a single hyperplane. In this case, a single line. So like, again, the hyperplane has dimensionality n-1. The dimensionality of this problem was 2D, as you can observe here, right? So like the hyperplane that I need in this case is a single line, correct? And yeah, we say that like this linear separable problem, right? Because I can separate the two classes with a single line. So like a linear solution for this problem already solves the problem, okay? Very well, but as you can probably imagine, I have more cases that they're not necessarily linear separable, right? So for example, what happens when I have a case like this where the data sets in at least in this 1D space, right? They actually don't present a way for me to separate them with like a single line, right? Or even more complex like this. In 2D space, you could have an arrangement of the data set that would like these concentric data sets, right? And what do you do for cases like this? Do you guys have any idea what we could potentially do here? For example, let's think of this 2D system, because we have been talking a lot about 2D systems, right? What could we do to solve the problem in a case like this? Any suggestions? Yeah, please go ahead.
Fitting a curve. something like a fitting like a polynomial curve when we do the
Fitting a
stats.
polynomial curve. So in this case, I wish we were in a classroom. So like I would ask you like to draw what you suggest exactly. But like in this case, would that mean something like this?
Drawing a circle, maybe.
Drawing a circle. Yeah,
Yeah,
that would be hard to implement with a single function, right? That would be hard to do. But fortunately, people have thought about that, right? And essentially, that's what the kernel trick does for you. So I'm not going to spend too much time on that, right? Because like talking about kernels would demand at least like another hour, and we don't have that much time. But the kernel trick, which is also an option of support vector regressor, right? And we're going to see that there. Remember that I told you that when we have a data set that's too complicated, right? I would suggest you to use linear SVR, right? So like linear SVR, it's what we have seen so far. That's what we have been discussing until this point, okay? But when you go to the sklearn library, you're gonna see that you have several options for kernel, right? And the kernel essentially stands for what type of transformation you want to do to your data before you fit the regressor, okay? Or like you fit the algorithm, the support vector machine algorithm, right? So for example, in this case, if I take this data and I apply a quadratic transformation, so like now I'm gonna get each one of these x's and I'm gonna, instead of using just x1, the data that I'm gonna feed or train the regressor is actually gonna be a kernel of x1, which essentially is x1 squared, okay? And here, now I have like a very clear way of separating this problem. So like I took it from like a no linear separable space to a linear separable space by using this kernel trick, right? And I think what you were suggesting before basically falls in this category, right? But like instead of fitting a more complex regressor, right? Actually, what we're doing is moving this data from this space where it's not linear separable to a space that's linear separable. So like we are doing a transformation to the data. So in this case, what we do is something similar. It's also a quadratic here, but like a quadratic in 2D space, right? So now in this space, you see that the orange points, they are separable by a hyperplane, right? They are separable by a hyperplane from the blue points, okay? And once again, so what's the dimensionality of this hyperplane in this case? In this new space? What's the dimensionality of a hyperplane that I need in this space?
Probably
Linear.
2.
Yeah, someone said 2, I think. So yeah, the 2 is correct because the dimensionality of this problem here is 3, right? Therefore, the dimensionality of the hyperplane that I need is n-1, which is 2. Perfect. Good. Any questions so far? You see that I overlooked several details here. So like, if you have any questions, I'm going to let you guys ask instead of me like pushing too much details. Okay, so yeah, Muletin, please.
Hi, Antonio. So I'm just wondering how we can know that the data are not linearly separable. So how, I mean, once we have the data, we have to make a decision, and yeah. So is there some ways we can test this, and or some indices or anything that can give us a hint that we have to do this kernel trick?
Right. I would say that the hint usually is to see that the linear doesn't work as well as the no linear, right? To the point that, for example, if we go, let me close this very quickly and come here to the main page. Can you guys still see my screen? Let me remove all this stuff. Can you guys see the main page of sklearn for SVR? Great, yeah. So like some of the things that we have discussed, right? So for example, the type of kernel. If you come here in the list of kernels, you're gonna see that you have linear as an option, right? So the linear is the one that we have been discussing the most so far, but you have several other options, right, of transformations that you can do to the data. So you can do like a polynomial transformation to the data, polynomial transformation. If you define what that you want to use polynomial, then you also have to define what's the degree of this polynomial, right? But you see that the default type of kernel is not the linear, which is the one that we have been using so far. The default actually is this radial based transformation. So it's radial based transformation, the name, which is a quadratic transformation of the data. And why is it the default? The default, it's because that seems to be the one that works the best for most of the case, which is like closer to what we did for this problem here, right? Which is like take the data from this configuration, right? And just apply a quadratic transformation to the data. So essentially like you increase the dimensionality by pushing things that are already like high value to like even higher values in this n+1 dimension, right? And usually that helps. And that's why the default, it's already the radial base, right? But at the end of the day, things that are going to help you to determine that are essentially like plotting the data, right? So like if you plot the data both for this case and this case, you're going to realize very quickly that it's not possible to separate this data with like a linear hyperplane, right? And start with like the default here, which is like the RBF kernel, right? Because that already does the transformation for you. But usually that's something that you're going to have to play with. Any other question before I...
Yeah, I have a small questions regarding what you told earlier about fitting these C parameters to support water machine model. Does it relate somehow to this well-known trade-off between bias and variance of most of the machine learning models? Like we should, does it somehow relate to this? Like whether we choose for the better fit to the training data or to the possible better extrapolability to some new data.
Right. I think you're going to get closer to that once we start talking about other methods that they tend to overfit to one specific type of data, right? And we're going to get to that in more details in the neuronal networks lecture, right? But I don't think, in just to like name it, we are talking about overfit here, right? So you say that your method is overfitting to the training data, right? And therefore it starts to perform poorly in the validation data or like your actual test data, where you say that those are the new sample, right? But no, I wouldn't say that this applies to like the concept of overfitting. Here, all we are doing is basically just to set what we call admissible with respect to errors that we're gonna make, right? And this implies directly like how many outliers I'm willing to make like a gross mistake in order for the general good, which is like to incorporate as many points as I can within this margin, which is defined by the black lines here in this case. So no, yeah, short answer, no, I don't think that's with respect to like overfitting problems. It's rather like how flexible or more rigid you want to make your model.
Yes, okay, thank you.
Okay. So I think that like it would be nice to have a little quiz before we get to the tutorial. So like I'm gonna activate. So please scan this. You guys also received the link to it in our chat here. So let me close this. Okay, so what was active? Ah, cool. So now how many answers we have for this? We have 11. So out of these 11 people who have answered the poll, 64% believe that they should keep the same level. Some people want more math, like about 20% want more math and 20% want less math, but we have roughly a Gaussian distribution here. So I think we're going to stick to the same level, if that's okay for everyone. Oh, okay. Some people want more math. Okay. You know, I have to say that I agree, you know, like if I was like in the position of the students, like learning how to run the code, I think that's there is a lot of tutorial out there, and like you can play with the numbers until you finally converge to something that's like it performs better, but like you need to understand what the numbers do, right? Which is essentially what we're trying to do here, like what these parameters they do for you, right? So you can choose then with less effort, at least, without just like going through like these all the possibilities for like hyperparameters, right? So yeah, but let's try to stick to the same level of math that we have been covering so far. And if you guys want more resource, what I'm gonna do from now on is to like send you links after the class, okay? So we don't spend too much time like explaining math, okay? So that's gonna be the approach going forward. And now let me find okay. Question number 1 of the quiz. Are you guys ready? So we're gonna do like last time. I'm gonna activate these, then please vote as fast as you can, and then we're gonna discuss if there is any issue, okay? So like activate. Please go there. So the question is, what support a vector machine? And then you have these 4 options as before. How many people we have today?
18.
Don't have.
And
Without-
could you
okay.
please explain how to activate this? Because I went to the link, but cannot just, I need to enter some password
Link-
maybe, or
The link is the
No,
same.
no. Yeah, the only thing that should be asking for you is if you want to put your name on it or if you want to be anonymous. That's all that it should be asking.
maybe I doing something wrong. It's like ask to register. Okay.
You can skip the registration.
Yeah, I assume that you don't need to do that. Pepe said that we have 15 people,
18 with
18.
excluding.
So let's say that
18.
a reasonable amount of people would be 13.
Yeah.
So like once I get to 13 answers, we look at it.
Primos, come on, guy.
Come on, guys, please.
This way I can see who is sleeping. Yeah.
Yeah.
There are 8 people sleeping.
Okay, 11. Just one more, 12. One more person. Okay, there. Okay, let's see the answers. So what's support vector machine? A supervised learning algorithm used for classification and regression. So most people believe that's the case. And a little bit of people believe it's an unsupervised learning algorithm used for clustering, right? So the correct answer is A, okay? And I believe most of you understood the correct approach here. So like, as you can remember, support vector machine works based on comparing what's the Y, which is the ground truth or like the true label, right? To what's the model output, which was the f of x. And then you multiply the two of them, correct? So this assumes that I have ground truth label. If I have ground truth label, it's a supervised learning algorithm, okay? So next question, activate. So for this one, what is the main objective of support vector machine? So we have been talking a lot about that, right? And I hope you guys can get to this one. Okay. So we already have 8. I'm going for 12 again. Nine, 10, very good. And here I should probably be more specific. I'm talking about support vector machine for classification in this case, okay? You got that from like the question, right? Which I'm talking about classification, classes. So like, yeah. Okay, great. Response. To maximize the margin between classes. That's correct. So yeah, so as you guys remember, right, like I'm not trying to minimize the classification error per se, right? Because if it was just a classification error, we are just shooting for any decision boundary that would separate the classes, right? Which that's not the unique component of the loss that I'm trying to minimize. But I'm also trying to find what's the optimal hyperplane, right? Which is like implies that I'm trying to maximize the margin, the margin between the classes. So people got it right. Activate. What's the support vector? How are we doing with time? Okay. I think you're doing well. If you guys understand all these concepts that we are describing here, then basically what I have to do in the tutorial is to walk you through like how to make use of the hyperparameters, like how to make use of these parameters that we give to SVM. Which again, like I personally think it's less interesting than actually learning what each one of these parameters are, right? Making use of them, you can just read the tutorial, but I understand people have different goals. So, okay, so what's a supported vector? Let's see what people answered. Okay, the data, so, oh, that's one, there was a huge split here, right? So what's a support vector? The data points that determine the margin of separation and the data point, oh, people are still voting. The data points located on the decision boundary. Okay, I think we should perhaps try to discuss this one. Okay, so someone who voted for A would like to try to clarify why you voted for A. Saying that A is the correct answer. I just would like to hear your rationale.
To be honest, it was a bit of a lucky guess, but I remember you saying about
I like honesty.
error. So that's kind of, you know, it was the choice between the top two. And I remember you talking about the margin of separation.
Right. Yeah. So like,
yeah.
you remember that we have three components, right? We have the hyperplane, which is like the one that goes in the middle. And then we have the support vectors, which are defining the margin, right? So like, if you guys remember, I always have, let me go back here very quickly. Right, I have the hyperplane and then I have two lines that run parallel. So the hyperplane is the one in the middle, right? And those are the support vectors, right? So like now if you go back to the question, the decision boundary, which is the hyperplane, right? The data points should not be located on the decision boundary, but they should be located on these support vectors, right? Which are the margin. Okay, is that clear for everyone? We don't want the points on this on the boundary. If the points were on the boundary, then you're talking about support vector regression, right? Okay. Is there any question about that?
I'm a little bit confused about what does it mean about the decision boundary?
Yeah, so the decision boundary is the hyperplane, correct?
Yeah.
So let's go back to this diagram because this is important. So
Yeah.
this is the decision boundary, right? Few lectures before, I gave you like a couple of options for decision boundary, and we said that all of them were doing the correct job, which to correct classify or separate the two classes. Correct? Good. So now the question. So again, keep in mind that this is the decision boundary, right? The question was, in support vector, what's the support vector? The data points that determine the margin of separation, or the data points that are located on the decision boundary, right? So like, if that was the case, the data points located on the decision boundary, I would say that I want the points to be here, right? So like, that's not where the support vector is supposed to be. The support vector is supposed to be defining what's the maximum separation I get between the classes, right?
Yeah.
Okay, so it's in the margin. Is that clear?
Yeah, thank you.
Okay, great. No, this is important. I'm glad that we managed to spot this misunderstanding. Okay, I think I had just one more. Okay, this is a very important one. So, yeah. In SVM, what's the role of the regularization parameter C that we have seen today? So the parameter C now is talking about the regression.
No. It's
I'm gonna go ahead with this
Mm.
one because of the time we have, right? So yeah, this is correct. So like it controls the trade-off. Okay, people are still voting. Yeah, it controls the trade-off between maximizing the margin, right? So like we're trying to maximize the margin and minimize the classification error, right? So like we are trying to say that like it's how much I want to make sure that I have as many points as I can, right? Like either within the margin in the case of the regression or outside the margin in the case of the classification, right? While minimizing the classification. Yeah, I think this was a poor choice of words here. It controls the trade-off between maximize the margin, minimize the classification layer. Right, yeah. I think that I should have framed this question as a regression problem instead of classification. Yeah, but the idea is the same, like that we are trying to find this trade-off, right? That as we described before, like so the margins are defined by the epsilon. So how many points I want to be either inside the margin if it's a regression or outside the margin if it's a classification, right? And how many mistakes I'm willing to make, either like minimizing the classification error, which is going to be defined by C, right? Or being outside of these boundaries in the case of the regression. So like, I think most of you got it correctly, although I messed up with the formulation of the question. But yeah, very good. Let me find just one more question and then we move on. Okay, maybe this one. And then we start with the tutorial so we don't get too late. So what is the difference between SVM for classification and SVM for regression? I can share all these questions with you guys later too. I remember that someone asked the last class. So like I can share both the questions and the answers. And then you can like retake this test as many times as you want. And if you still have questions, we can address. Okay, if we get to 10 people answering this, I can move on. Okay, let's just move on for now. Most people got it right, which that's the support vector for classification, minimize the hinge loss, right? So if you guys remember, the hinge loss is that product between what's the model output, the f of x, and what's the ground truth, which was the y, right? If both of them are matching, right? Therefore, I say that they have the same sign, so they're both -1 and 1, or both are 1 and 1. Either way is going to be the product is 1, and the hinge loss is 1 minus the product of y and f of x. So if they are green, it's going to be 1, therefore it's 0, right? So like, yeah, so you're trying to minimize the loss of this hinge loss, right? And in the SVM, you're trying to minimize the difference, right, between these points that are inside the boundary and yeah, the points that are inside the boundary, they are not considered hinge loss, right? And for that, you can use anything. It could be like in the example that I showed to you guys, I wasn't using the mean square error, I was using mean absolute error, but essentially they quantify the same thing. Okay, so let's go to the tutorial. I feel like at least we managed to spot one thing that needs to be addressed, which I hope I managed to answer the questions, right? And then we can discuss that in further details, like if you guys still have any pending questions. So now, Pepe, I think you changed the name of the Jupyter Notebook, right? But like you should see that there is a Jupyter Notebook called Tree Height SVM somewhere.
Yeah,
which I hope you guys can access.
Yeah, I also paste in the page, and please be sure you do the typical git pull and rsync in the virtual machine.
So I'm gonna give like
Actually,
2 minutes.
Yeah, I also insert in that Jupyter Notebook also the pip3 installation procedure for install this 3.4 package. Should be the first line.
Cool. So just a few more minutes perhaps, so to make sure everyone is in here. What do you think, Pepper? Should I go ahead or wait a few more minutes until everyone managed to find the Jupyter Notebook?
You find out? Anyone find the Jupyter Notebook was able to open? Yes, no? 1 second.
Yeah. I feel like we're doing okay with time so far. So. In the meantime, if you have any questions, please feel free to ask while other people are loading the Jupyter Notebook.
Sorry, and after we open this Jupyter Notebook, should we run this code at the beginning when at the section getting the data set, or it's not necessary now?
No. The data you should have already done 3 weeks ago. Is still the
I assume
same?
you guys.
Okay.
Yeah.
Is the tree height, okay? So the only thing that you should be able to access is the pip installation. Wait, I'm trying to open the same.
Mm-hmm.
Let
So
me share
this
one.
data is the same data that
Yeah.
Pepe described in the
Yeah,
first class.
they should have all of them. Yeah.
Mm-hmm.
Yeah, give me 1 second the screen.
Yeah, sure.
So everybody should be able to see this one in particular. If you go under the typical MySC data exercise, you should be able to see Jupyter Notebook, tree height for this one. Okay. And this is the one that you have to run the pip installation in order to be sure that you get all the different Python package.
Mm-hmm.
Of course, you have to do in the terminal, this one, the bash terminal.
Did I use PyTorch?
I think it was in the anyway, it's not a problem if it's there.
Yeah. I mean, I'm gonna use PyTorch for other.
Yeah,
sure. Go ahead.
I have the notebook open and ran that pip3 line, and I failed on the PyTorch install. It sounds like it doesn't matter for this lecture, but
Right, yeah, you should need that. And in fact, like in the class that I use PyTorch, I give the proper command. I don't think we should be using pip install by PyTorch.
It was working. They didn't use any cond environment. And I saw that all the importing was working fine.
Okay.
So that's why I used the pip3. So I ran the full script that was working fine. At least not the full script, this one.
Right, yeah. Yeah, for this one, you're not gonna need PyTorch, at least. But if it's failing, then we need to address that, like,
Okay.
before we get to the neural network stuff.
Okay, everybody's there. I stopped the sharing.
Okay.
Yes, I'm sorry. And if I have got this file in the exercise directory, but without this 2023 prefix with it, it may be some old file. Yeah.
Have you done the git pull?
Yes, I've run it, but maybe it was unsuccessful, and I had got only. But is this a big difference between this old and new, or is it possible to use this old file?
Okay, I'm sending. I'm posting here in the chat. But if everybody do the git pull, you should get it, and they are sync. Anyway, I will post it the file here. I think I can also send it.
Yeah, I mean, you can just follow along. You don't need to run this because you're gonna get exactly the same result that I'm gonna get. So like, doesn't really make any difference. So for the sake of time, I'm gonna go ahead, all right?
Yeah.
Okay, cool. So things that probably you haven't seen yet. So like, I believe pandas you have worked with, NumPy you have worked with as well, right? So since Pepe didn't talk about, I mean, he gave you the recording, but like we didn't run it together. So we're gonna be using this package called sklearn. Have you discussed sklearn before, Pepe?
No.
No? Okay, great. Yeah. So like sklearn essentially is this library, right, that we're going to be using for that. And within this library, you guys please like feel free to explore that on your own later, right? But you have several things that are meant for like also machine learning, right? So for example, random forest is part of that package. So for example, you see that I'm importing random forest here as well. SVR, the support vector for regression is also inside of this family, like inside of the umbrella support vector machine, right? And you have several other things, even like including for neuronal networks, which I'm gonna try to discuss that also like when we get to the neuronal networks part of the lecture, okay? Everything else here you should be familiar with. So this is the function that we're going to be using for plotting, right? So like we're going to be doing some scatter plots in a little bit. This is a package for like computing some statistics that I think that Pepe likes to use it. I personally, I use some other metrics, but like, yeah, it's also here. Okay, in Rasterio, probably Peter discussed that, or was that Francesco?
Yeah, mainly Francesco, and yeah, but he's also combined with the Peter class, yeah, for dealing with raster data, yeah.
So probably you guys know that better than I do. Yeah, so very good. So the data is exactly the same data that we discussed before, right? So like that's the data that Pepper introduced in the previous class in the first 15 minutes, right? So like I'm not going to spend too much time on that, but the general structure, as I hope you can remember. So that's the X and Y coordinates, right? Of where that tree had its height recorded, right? We have this variable height, which is the height that's estimated from this satellite image, right? And then you have a bunch of other variables here that Pepe already introduced to you, right? So to the best of my recollection, forest height was the estimation that was given by another method, correct, Pepe?
Yes, the forest height is returned by 6 algorithms, and we are using the mean of these 6 algorithms.
Perfect. Yeah, and this one is already given in meters, while this
in meter. Actually, it's not meters; it's meter times 10.
Okay, meters. Well, that's a funny metric, meters times 10. But yeah, so that all right. And this is the estimate given in centimeters, I believe. Right?
Sorry, 1 second.
The age.
Yes, yes.
Okay, very well. Yeah. So like the first thing that actually Pepe does, because I got this part of the data plot from his script, right, is essentially to first plot the histogram that shows us the distribution of these tree heights, right? So we are plotting the H variable from this Panda variable, from this Panda data set, right? And here you're observing what's the distribution. So you see that most of them, it's in the scale of like 2000 centimeters, right? And then you have like several small, very short trees, or perhaps this was just vegetation. Did you ever get to a conclusion to why you have like such a spike in year 0 here, Pepe?
Yeah, because, okay, so as you can see, the mean is around 20 meters. So it's like usually the tree are high. And the spike over there close to 0 is because many points, they return the ground level. So they're close to 0, 1 meter up and down, you know. So you can have many points that are spike into the ground. And then you have some other that are even more bigger than 60 meter. Okay, so and usually the highest tree is something like 70 meters. So that's why in the following line we remove everything that is above 70 meter.
That's correct. So that's the next thing that I was going to discuss. So you see that like here, what Pepe is doing is essentially to select from this table, specifically the estimate of the trees is 16 centimeters, everything that's below 7,000 centimeters, or therefore like 70 meters, right? So now these variable predictors, which are going to call the predictors selected, right? Predictors cell, is going to contain only samples that are below the 70 meters, right? And what Pepe does next then is to select 100,000 cells, like rows of this table, right? So like we're only going to analyze 100,000 collected samples. Okay, so Pepe very cleverly then does this transformation from centimeters to meters. Thank you, Pepe. That's very, very useful. And now you see that like the length of this table now it's 100,000 because we had done this sampling from this table, right? And here we are plotting again the top 10 rows that you observe. So you're going to observe that now we have this height in meters, which we're going to call HM, right? And which is very nicely already put here for us. I think this is meter, Pepe, because you see that the forest height is also like in the same magnitude now.
All right.
10, 22, yeah. So it's forest height was already meter. Okay. Very well. So like that's how our distribution looks like now. So you see that's now capped by 70, right? So it looks a little bit more normal, right? Which is perfect for us. We really want to have that like for any type of machine learning algorithm that we're going to be discussing from now on. We are always going to try to get as normal distribution for output in variables as we can. So we're going to be discussing like types of transformations in the next lectures as well. I see that there are questions.
Antonio,
please go ahead.
I mean, now why we have now forest height for tree height in integers? So maybe.
So the forest height is coming from the Metanson estimation.
Yeah, but I think you should divide it with 100 dot. Yeah, then you will get you will not get the integer, but you will get centimeters.
No. The forest height is giving in meter in the Metanson product. Okay, so when it's divided by 100, is getting HM. Okay. So he maintained the floating point type. Yeah.
Okay. Yeah, yes. So, yeah. Sorry.
No problem.
Yeah. Okay. Good. So now we have some distribution, right? So let's keep in mind that what we're trying to beat here is essentially this prediction that's being given by the 6 algorithms that Pep described in the previous lecture, right? So if you try to compare what's this prediction that's coming from the previous method, right? The 6 algorithms with the ground truth, which is like the HM variable for us now, we see that we obtain a distribution that sort of looks like this. It's kind of discrete because forest height was as I think the previous person was discussing, it's in integers, so it's not a float, right? So that's why you see that there is sort of like vertical lines, right? But the R-square between the prediction, which like this prediction that's being computed by the 6 algorithms, and the true value is about 0.46, which is not terrible, right? But also it's not very good. So like we're gonna try to change our algorithms here, like to support vector machine for regression, and try to see if we obtain an R that's greater than this. Okay. All right. So let's start doing some manipulation. So like very well. So now the first thing that we want to do is basically to split the data, right? So like first, I'm going to remove some of these variables that we don't want to use. So for example, what's the ID of the sample? Like if you see it here, I have the ID of the sample. That doesn't mean anything for us, so we shouldn't feed that to the method, right? The age, it's the thing that we're trying to predict, so we shouldn't give that as input to the method, because otherwise the regressor might just start using that information instead of making use of the rest of the features that we're giving, right? So like we're going to remove that as well. Oh, you guys are familiarized with the command drop, right? Like in pandas, but if you're not, drop essentially stands for removing that from the table that I'm going to be working with, right? Like I'm purging that column from the data. Okay, so like I'm removing ID, I'm removing age, and I'm removing HM, which is like the transformation from like centimeters to meters, essentially. And here I'm also removing X and Y, which were the coordinates, right? And forest height, because forest height is also like estimates that's coming from the 6 algorithms. We don't want to use that as information. We could, right? So it will be built in on the estimate that's given by the 6 algorithms. But for this experiment here, we're not going to use that. Okay.
Sorry, Antonio, one point to address to everybody. The HM is coming from the 6 algorithm, the mean of the 6 algorithm. Rather, the forest height is the data set that we are trying to beat because it's coming from another publication, another estimation.
Oh, okay. I see.
So, yeah. So the HM is our LiDAR mean, JEDI mean coming from the mean of the 6 algorithms. Okay.
Ah, gotcha. Okay. I see. So forest height is what you're trying to beat because it's coming from another publication.
Yes.
Okay.
Yeah. Okay. Yeah.
Okay, that makes it more interesting then. All right.
Yeah.
Okay, cool. Yeah, so that's a publication. Let's keep that in mind. So like people managed to get an algorithm published, and we are gonna try to beat that with like using supported vector regression. How cool is that? Okay, cool. Very well. So like you're gonna see that tree height, which like we're gonna consider that as like our ground truth in this case, is gonna be obtained from this HM variable that we just created. So like that's what we're trying to train our supported vector regressor to approximate. Again, we have ground truth label, therefore we are using this in a supervised learning framework, right? Which is what supported vector machine can do for us. I hope like we always manage to keep that in mind. Very well. So like now what we're gonna do here, right? I'm gonna, because as you guys remember, supported vector machine, one of the issues it has is that it doesn't scale very well for too many samples, right? To the point that I said that if you're gonna use more than 10,000 samples, probably should use something else, like just the linear implementation of supported vector machine. So what I'm going to do is to do that for like a much smaller data set. So I'm just going to be using the first 20,000 samples. Okay, so like that's essentially what this command is doing. Can you guys see, or should I try to zoom in a little bit better? Okay, good. Yeah. So yeah, so this function, train test split, it's going to separate for us a couple of samples for training purpose. So we are going to fit the supported vector regression on this section of the data set, right? And we're going to have a test data set as well, which is going to be like another fraction of the data set that's just going to be meant for like evaluating how well our regressor is doing, okay? So that's what we're going to do by default. Let me show you guys as you learn. So you see that's like there are several other parameters that you can pass to it, right? So like right now we're passing just the array, right? If you come back here, we're passing the array data, right? And we're passing the Y, which is like the ground truth label that's associated to each one of the samples, right? But you have more parameters that you can give. So for example, you can ask the train splitter to train test split to also shuffle the data. So like if you believe that there is some degree of like organization in the data that you don't want to bias your method towards, right? So let's say that like the first few samples of the data set, they are just shorter trees, and then the end of the data set are like larger trees, right? Because for whatever reason, like during the data collection, there was such a bias. You don't want to train your method just in short trees and then evaluating larger trees, because the method probably is not going to be able to generalize to these held out section, right? So like you want to like mix a little bit, right? And another thing that you're going to specify, it's what's the test size, right? So like the test size, which we didn't pass here, it essentially stands for like the fraction of the data set that you want to use for running the inference, right? So you see that here, the test size by default, the test size by default is 0.25%. So like that's 25% of the data that we have, which is roughly what you're observing here. So you see that the number of samples allocated for training are 15,000, right? And the number of samples allocated for testing is 5,000. Okay, any questions so far? So far we have like separate what we're going to be trying to predict, which tree height, right? We have removed all the columns or features or predictors that we don't want to use as inputs to the model, right? And now we have split this data in both training and test set, okay? So we're going to fit the model to the training set, and then we can run evaluation to the test set. Okay. Okay, very good.
Can I
Yeah,
ask
please.
a quick question? In this line where you say train test split, you're using a subset of the data, or?
Correct. 20,000 samples. Yeah.
So, but that's not random. Is it randomly sampled then at this point? Or are you randomly sampling from the subset?
So we already randomly sampled here, right? So like remember that you're doing dot sample. So this data set is already shuffled. Yeah.
Okay.
Okay.
Thanks.
And on the top of that, you see that the default for like the train test split is shuffle equal to true. So like it shuffles once again. You're shuffling already shuffled data set. So double shuffle. Okay?
Double shuffle. Okay.
Double shuffle, if you will. As shuffled as it gets. Okay. Any other questions? Are we doing with time? Okay. Perfect. So like now let's move on. So now we are gonna perform like some scaling of the data, right? So like that's a thing that is gonna matter way more once we start talking about machine learning, like in the neural networks type of direction, right? But the min-max scaler is going to scale this data for you. So maybe I could plot. Let me see if this is. Let me plot some samples. I should have plotted like some samples before and after the scaling, right? But what the min-max scaler is going to do is to do the normalization of each one of these columns for you. So by default, because each one of these columns, right, that we have in this data set originally, you see that they are ranging like for example, this variable, the sexol, right? It's like 10, 12, like 15 and so on. Now the Chelsea is like in 2000, 3000, right? So like the magnitude is different, but the difference in magnitude doesn't matter, right? So like the difference in magnitude doesn't matter. It matters with respect to each value within the column, right? So like if it's like going from 1000 to 2000 or going from 0 to 1, the only thing that matters is like the relative magnitude within the column, right? So I could rescale this thing that's going from like 1000 to 2000 to be between 0 and 1, like, and that shouldn't like necessarily be a bad thing. And actually it helps, because now the weights of this regressor that I'm trying to fit, they're not trying to compensate by these different magnitudes that I have in the inputs data, right? They're just trying to use these small changes that I have in the data after the normalization and try to find the weight that makes the best out of the information that's being provided by that column. Okay, which also acts towards the regularization component of the method, right? So we would be trying to penalize a weight to be as small as possible, right? Because you guys remember that I have that term here, right? Which part of the loss. So I'm trying to minimize the magnitude of the vector that is composed by the weights, right? And if I have like another variable here, let's say something that's going like 10 to the minus 4, right? Like was a very small variable, but I need to correct for that because this other one is like in the thousands. I would have a huge discrepancy between like the weights that are composing this vector. So like that's why we do that. Okay. Very well. So like here we're going to scale that. So like now each one of these columns, which were originally going from like whatever value to whatever value, they're going to be mapped to be between 0 and 1. Okay. So if I plot X train, you should be able to see that. Hold on. I'm going to add another column here. Yeah. So you see that all the values now they're ranging between 0 and 1, right? So like that's essentially what the min-max scaler is going to do for you. Very well. Now we get to finally to the supporter vector regressor, right? So here I'm just calling the default for all the parameters, right? So let's see what are the defaults and what I'm going to be using here. So this is the object as supporter vector regressor. If you want to take a look at the definitions, so we're going to see that the first parameter that we get is the kernel, right? So you guys remember that we discussed the kernel a little bit earlier today, right? Throughout the classes, we have been using the linear kernel. So essentially, it's just a linear transformation of the data or no transformation at all, okay? But the default, it's actually this RBF. So it's this radial basis function, okay? That basically increase the dimensionality in a no linear way, like with a quadratic function. All right, and I can give more details if you guys want later. But you have several others. So like today we're going to be playing with the default RBF, which is what we're going to be using for the first experiment. And then we're going to see also what changed when you go back to the linear, okay? Then if you're using polynomial, you also have this degree, which we're not going to be using. But you guys remember that we saw two important parameters, which were the epsilon, right? Which basically specifies the margins, right? You guys remember that the margins were defined by this epsilon. Where is, yeah, here. By this epsilon, right? So like people talk about that as being like, what's the size of this tube, which encompass either the data in the case of the regression, or like the tube that's in between the data sets in the case of the classification, right? In this case. But we are running regressor, so we're talking about the tube within most of the points they should be included. Okay. Very well. So we're going to be using the default for now. So like the epsilon in this case is set to be 0.1. Okay. And then we have the other parameter, which is the C, right? Which is like it's the C that's going to be determining how much slack I'm willing to give to the regressor, like how many points I'm willing to allow to fall outside of this tube that's going to be defining the regressor per se. Okay. So in the default case, let's see what was the default case. In the default case, C is equal to 1. All right. So, okay, we're running this thing as default, right? So now the next command that we use is to fit the regressor, right? So like one of the attributes of this class SVR is the fit command. So it essentially stands for like, okay, now given this data, X-train, and this set of labels that I'm giving to you, fit this set of weights W that we have seen so far, like many times, right? That approximates as well as it can this tube that's gonna include as many points as I can. Okay, so that's gonna be what this SVR fit does for us. Next, what we do is to compute the score. So like the score essentially is the coefficient of determination, right? So the coefficient of determination is the R square. The R square between what's the model output, right? So like what's the prediction for the X train and what's the ground truth, which now is included in Y train. Okay, so like we're going to be computing what's the model output given these features that I'm passing through the as in the shape of X train, right? And comparing that to the Y train. So very well, if you do that, so let me run this. It takes a couple of seconds. So like, don't worry if you're gonna need to run on your side there. You can do that like on your own later. Let me import this function for plotting. Takes a couple of seconds. And then in the next line, they do exactly the same thing, but now for this held out data set, right? Which is the data set that was not used for training. So essentially it would simulate for us what's gonna be the performance of this method when we include new samples. So like, let's say that because after you have trained your model, right? You want to deploy that in the wild. So like you're going to start seeing samples that are outside of what you have trained the method on, right? And hopefully you're going to perform like similarly. And that's generally what we observe. So you see that the R square for the test set, right? It's not that far off from like what's the performance of on the training set, right? So this method is like performing reasonably well. So if you plot the R square, the scatter plot, right? We see that for the default configuration, right? We already obtain an R value of 0.48, which if you guys remember, this method, right, which was the published one, managed to get 0.46. And like we did absolutely nothing fancy here, right? And we already managed to get 0.48. So like we basically just got this method off the shelf, like as it comes. We didn't set any parameters to it, like we used the default, right? And already managed to beat the performance of the published method. That's quite remarkable, I'd say, no? Any questions so far?
I have a question for you guys. What does mean that the training set is 0.23 and the test set is 0.22? Is something acceptable or not, and why? Antonio say a few words, but he didn't go deep, so I want to. So if we have the training set very high, like 0.40, and the test set is 0.22, what does it mean?
I would suppose the result which we got now, it's pretty good because the accuracies are very close to each other. But if they deviate a lot, it would mean that the model is overfit
Overfitting, perfect. So it's too good for the training and is performing bad for the testing. So we want to have always, you know, something very close between training and testing. Okay. This is what does mean overfitting. And usually support vector machine doesn't overfitting because it's like a bunch of regression line through the points. Okay.
Giuseppe,
Yes.
what's the difference now between this R square down? This is all data on the scatter plot. And this
no, the difference here, right? So this was R square, right? And this is R. So this value should be the square. This value that you're showing here should be the root square of this value, essentially.
Okay.
Okay.
Yeah.
We are doing that just for the test set.
So we are making our prediction. We are comparing our prediction with the forest tree height from Matt Hansen prediction. Okay.
Yes, yeah.
Okay, so we already see that we are getting better, and we will say why, not only due to the method, but due to the predictors also. Okay.
Can I ask, what is like when we do this type of test, what is a good threshold for R squared when, like, what is good or what is the time when you have to add like more predictors or like get more data to fit the model?
Okay, it's very depending from some phenomena. You know, there are some phenomena that are very difficult to predict due to the chemistry behind the phenological status and so on and so on. So, you know, if it's very difficult to predict because there are a lot of hidden predictors or hidden phenomena inside, then, you know, 0.5, 0.6 can be acceptable. Rather, if they are very well known phenomena trade with a really strong predictors, then you have to overpass in the 0.8, 0.9 R, you know.
But I would say,
for example, in your
also...
case, the chemistry, water chemistry, I think is a very low. So it should be always below. No, always, yeah. If you can eat 0.6 is already a good, yeah, I think.
Yeah, it actually depends a lot on like what's the problem, right? So for example, I have some friends that do economics, right? And they build predictive methods, for example, for forecasting like clients' purchase behavior, right? When is more likely that you're gonna make a suggestion, the client is gonna say like, oh, you know what, I want to buy that product that you just recommended to me, right? When you're talking about like economics, if you manage to like have an R square between like what you're predicting, right? And like not what you're predicting, but like how much more you're going to be able to increase your capacity of like estimating what your client wants to buy. Like a R square of 0.1, it's already great for them. They're like jumping like up and down of happiness, right? Because if you can increase by 5% your chance of making a sell, right? Like of manage to induce someone to buy something, that's already extremely significant, right? Now, when you're talking about a R square of like 0.98 in medicine, people are like, oh, this is garbage, don't use that. You know, because like if you don't have 100% of chance or like 99% of chance of making a prediction correctly, people don't care about it because like, you know, like this I still have a chance of like failing and perhaps like recommending something that might kill someone, right? So like it's very relative.
Thank you. Yeah.
Okay, so maybe we can move on a little bit. So like let's see what's the impact of other parameters, right? So like we have been using just the default so far. Remember that the epsilon was 0.1 before, right? Let's see what happens when you make this margin even like narrower, right? So like now we're saying that we wanted the model to be fitting a margin that's even tighter. So in theory, if you make the model tighter, you're saying that you want this most of the to fit a model in which most of the points fall within a very narrow margin, right? So like the model has to be extremely precise for that model to finally say that it's managed to fit the data, right? So we are going from 0.1 to 0.01, right? What do you think you guys think is going to happen while this thing is running? So like, let's compare. So this one was 0.23058, 0.23, 0.06. Yeah, didn't change much. Yeah, so like apparently we didn't need the epsilon that big, right? So like we managed to reduce the epsilon. So like the margin is more narrow now and didn't change much the performance, right? But now let's see what happens when you increase the flexibility of the method, right? Like now you're gonna say, remember that before you're using C equal to 0.1, which was the default, right? So if I increase 0.1 to 2.0, 0.1, no, sorry, was 1.0. That was the default. Where is it? Yeah, C was equal 1.0. Yeah. So like now we are doubling the C, right? And I'm not gonna run this because it's gonna take a while, but like you keep this number in mind and then we see what changed. But like you see that's like this is 0.23 now, right? So like finally we managed to get like a small improvement by increasing the C. We saw exactly the same behavior once we are observing the study case with the house pricing in Boston, right? We saw that like, okay, you can make more mistakes with respect to try to fit the outliers, right? And by doing so, you manage to give more flexibility to the method, right? So like we managed to get the line a little bit better adjusted, right? And we are observing exactly the same thing with the C here. So like we are allowing the magnitude of the mistakes for the outliers to be bigger, which is it's fine in this case, because we still get most of the points within the margin. So like that's good. Okay. And now we went from 0.48 to 0.49. Okay, so like, and we just explored two parameters so far, which was the epsilon, how narrow the margin is, and the C, which like how much slack are we willing to give to the outliers. Okay. Now, in this other example, I kept both the epsilon and the C as before, so epsilon 0.01 and C equal to 2, right? But I changed it from the kernel that was the default, which was the quadratic kernel, RBF, to now to use the linear kernel. And you see that the performance dropped quite a lot, right? So I don't remember who was asking me, like, how do you estimate if it's like quadratic, a no linear problem versus a linear problem, right? Now we can see clearly that like estimating the tree height seems to be a no linear problem, because in fact, using the kernel that's no linear, the quadratic kernel, we have like a better performance than using the linear kernel, and by quite a bit, right? So you see that's like, it went from 0.23 in this case, almost 24, to back to 0.18. So like that's a substantial decrease. Probably this method here would perform worse than the forest height estimates given by the other publication. Okay. Any questions here?
Yeah, Milutin. Any question, Milutin?
Yes, so I just wanted to check if I can interpret it correctly. So when we reduce the epsilon, we didn't gain any improvement in accuracy, yeah, in our sphere. This means actually that our data are already well separated from one another. So we don't need to reduce further the error, the margins, yeah, because if we make it smaller and we don't see the improvement, is this a correct interpretation?
Not really. So like first, the first thing that you said there was with respect to separation, right? So like remember that separation is for classification, and what you're doing is a regression, right?
Oh gosh, yeah.
So we are trying to get as many points as you want within the margin. So like within these lines that are representing the support vectors. Okay, so that was the first thing. Okay, so now remember that what we did essentially was to play with this margin. So like it was 0.1 originally, and then we went to 0.01. So like we decreased further the margin, right? So this is going to depend a lot on the distribution of the data, right? Like the distribution of the data, the original data is high dimensional. So it's not like simple 2D like this, right? So like it's hard for us to visualize that, right? But like in the case here is essentially that like making the margin more narrow didn't change much performance. So we could be basically like changing how narrow is this margin here, right? Probably it wouldn't change the performance of the methods by much, because the actual main issue is the outliers. Like the outliers, they're just like really messing up with the performance of the regressor, right? So the thing that actually made the difference was by allowing some slack. So like saying like, you know what? These outliers that you have, don't worry about them. Like I'm gonna give you some slack via increasing the C, right? So like then instead of like trying very hard to just fit this regressor, taking in consideration as many outliers as I can, right? Increasing the C allows us to basically discard those and say like, I'm willing to have a bigger error dose to these outliers. So it's fine, you know, and like focus on on getting as many points as I can within the margins. So that's the interpretation. Does it make sense?
Yes, yeah, thank you.
So Antonio, once again, can you go back to the slide? So the epsilon is the distance between the black line and the red line?
Correct.
Correct.
For both for up and for down. So like
Down.
in this case, epsilon is equal to 5. So epsilon, so this prediction plus 5 and this prediction minus 5.
Perfect. Rather, the C is the distance.
The C basically implies the magnitude between this margin and these outliers.
Perfect. Yeah. So when I change the epsilon, it is also changing the C.
The epsilon, so they are two free parameters, right? So like if I decrease the epsilon, for me to be able to compensate for the outliers, I would have to increase the C even more.
Okay,
yeah.
Perfect. Okay.
Yeah. To say that's like I have exactly the same performance still.
Okay, good.
Can I ask how about if we have the epsilon very large, we also have the C very large? What would that do? Like if the epsilon is so large that it already encompasses all the outliers, but then you still have a large C.
Okay, so if you have a very large epsilon and a very large C.
This is just like I'm just imagining like if we turn the epsilon really large and then you still have a really large C.
Yeah, let's think about it. Let's think about it. Let's say that's like now we have, let me see if this is working. Yeah, okay. So let's say that you have a very large epsilon, right? So like, I'm gonna allow this epsilon to come all the way here. Now the error, it's very small, right? But the hyperplane, it's now here, right? What do you think? Is this hyperplane, this regressor, doing any better than this regressor with the narrow epsilon? No, because like if you actually compute the R-square between these points and the ground truth, which are like the blue points, right? Probably you're gonna see that the R-square here is lower than the R-square between this curve and the ground truth, right?
I'm thinking, but I'm trying to think that if in the case of turning a large epsilon, does the C automatically decrease, or do you still have to change?
It's a free parameter. Yeah, you still need to change that.
But like if like we turn the epsilon to include basically all of the numbers, all of the data on the plane, then what does the changing of the C does?
Yeah, if you include all the points, then the C basically has no role, right? Because you no longer have outliers.
Okay. Got you.
So you have the normal regression.
No,
No?
No, you
Just-
wouldn't have a
it's-
normal.
It's nonsensical. Maybe model will be if everything falls inside it, just a constant like this.
Right. I could have another fitting curve, right? Like let's say that the epsilon is very large. Like if the epsilon is very large, I could have
50 and
the
then-
supported vector here, right? And like the hyperplane here. Like this model is extremely bad, right? So like you don't want to have a large epsilon.
Yes, Antonio, and the opposite situation, if we set epsilon to 0, what does we get at
Oh.
this case?
The epsilon equal to 0. So like let's imagine that now we have a very narrow epsilon, right? So like probably an epsilon that's gonna try to get as many points inside as we can, right? In this cloud is hard to estimate, but let's say that probably be something that's gonna look like this, because I think that's the highest density of points right there, right? So like the hyperplane would be here in the middle. Okay, so like it's gonna focus on the highest density area and it's gonna discard everybody else, right? So like that would be very difficult for the model to get a good performance there, because then you're focused just like on a very small set of points. So like it's a little bit of work to find the correct set of parameters. That's why usually you have to combine that with some sort of grid search, where you go like over like, okay, I'm willing to have this much error in my prediction, right? So like you set the epsilon as something acceptable. So for example, when predicting the house price, that was the task originally, right? I say that's like, okay, when I'm predicting the price of this house, if the price was like $40,000 and I make a mistake by like 5,000, that's acceptable. So like I'm saying, first I'm setting what's acceptable for me. And like my acceptance of the error was 5,000, right? And like with that now, let me play with the C. That's gonna get me something that's reasonable. And it still doesn't deviate too much from like having a good R-square. So all these three parameters that we're discussing here, they have to come combined with like some knowledge about the problem that you're trying to model, right? Which is like the part that it's gonna come through experience with you guys. Okay.
Yeah.
So like just for the sake of finalizing these, right? So like we made this prediction, right? Just on the table. So like you guys already saw the raster IO option of like bringing this back to like a map looking, right? So that's essentially the prediction that you're getting using the this approach, but bring it back to the map prediction. So essentially what you're observing in orange would be like higher trees, right? For this specific location in the map. I don't see many blue points though, which would be representing like shorter trees, but like, yeah, you can see roughly the location of these trees. You want to comment anything else about this plot, Pepe? Probably you have more background on that.
Yes, we are still getting a prediction that is very low in R square, so it's 0.2, 0.23, so it's not real well accurate. So if you're running the random forest method that I presented in the video recording, you can find the syllabus, the link over there. You can see that we are eating a better performance, and later on Antonio is going to use the same data set to do with a neural network.
I think you're reporting the R there, no?
I think so, yes. So this plotting procedure is very long. Not the plotting, but the prediction is very long in time. Took even more than 10 minutes. So we are searching for something better for making the prediction, because making the prediction to the raster is quite heavy. So we are working on find something faster.
Right.
Yeah.
So now like to the part of assignments, right? Like things that I would like you guys to play with, right? So for example, we have discussed a couple of options. Some of them we even like already played in this tutorial here. But for example, we talked about perhaps like a stronger regulation, right? So like, for example, some of the other parameters that we didn't play with, it's like the how much tolerance are you willing to have, right? Like with respect to the stopping criteria, that doesn't seem to matter a lot here, because like you see that these methods are still converging quite fast, less than like a couple of seconds. But what happens if you make this method even like tighter, right? So like I'm willing to have a tolerance that's even smaller than this. So like 10 to the minus 10, for example, right? How much that would impact on the timing of the fitting of the model versus improvement in performance. So that's something that's like you guys can play with, like as an assignment, like a homework, right? You can see what's the impact of like increasing the C, right? We played with 1.0 and 2.0. 2.0 apparently already gave us like a better performance, right? In terms of R square. Would that improve even further if I keep increasing the C, or does it start like showing some damage to the performance? For example, here we are increasing the C, it passed to the peak, right? Of like how many points we managed to include within the margins. And then at some point it starts to go down, right? But like by no means we explore the full spectrum. So like maybe you guys can play with some C and see if that gives us even better performance, right? And different kernels. So we played with the linear kernel and the quadratic kernel, the RBF. But we have more interesting kernels in this list. Not more interesting, but they're also interesting. For example, the polynomial kernel, right? So like here, we are not just like doing a quadratic operation to the data, like as some sort of transformation, but actually you have like a more complex polynomial expression, right? So like you could have like a polynomial of degree 3, 4, or even 5, right? So make the kernel even more complex. And you know that's like increasing the complexity of the kernel might help you to put the data in a space where things become easier to model, right? For example, we saw some cases here that's like by doing this operation with a different kernel, we managed to move it to a space where things start being easier to separate, and like works in the same direction for regression as well. We might be able to put this data in a space that's easier to fit with like a simple line, okay? And then I put this quote here that was given by one of my professors in like advanced computational vision, that he used to say like, give me enough dimensions and I'll classify the whole world, which essentially stands for like, okay, yeah, can I classify all the objects that are on my table right now, right? Probably I can, but it's becoming harder and harder for me to differentiate between like, what's the difference between a mug and a cup, right? Like I have to need more features if I want to differentiate those. Differentiating a cup from my cell phone is easier because like the shape's quite different. Now when it goes from like a cup to a mug becomes harder, right? Because we have like very fine features that separate those. Now, what's the difference between mugs? You see, like as I keep increasing the complex of the method, right? I have to have more and more features, right? And that's essentially what we're experiencing in machine learning nowadays. Like we're getting more and more data, more and more feature from that essentially also increase the demand for more and more complex methods. That's why, for example, we don't see supported vector machine being used a lot like in machine learning nowadays, right? Because those, they don't scale well for like the amount of data that we have to handle nowadays. That's where neural networks, they come in. Okay. I put this thing here like for you guys to play if you want. So like supported vector regression is using this implementation from sklearn. But if you want to see how these things, they actually work like behind the scenes, I put this implementation that's done from scratch, which basically implements what we saw in the lecture here. So like all of this that's implemented here, I put in this little script for you guys to play with in case that you want to see this thing converging, which I think is kind of cool, but I'm gonna leave that for you guys to play. Okay, I think we should definitely stop for a break before we move on. I'm gonna stop sharing now.
Okay.
If you guys have questions, like I'm gonna be hanging around here during the break, so feel free to come back a little earlier and ask your questions. Okay.
So we come back at 05.
All right. Okay. Here. Where did I stop? Okay. So we're going to be talking about intro-to optimization now. How much time we have? 40 minutes. That's right?
Yeah.
Okay. All right. So, okay. Now let's turn the chapter, right? So like we have discussed most of the things that we wanted to discuss about supported vector machine, right? Like both for classification and regression. We did some experiments with the regression case. Now we're going to move on to like other types of algorithms, okay? So I believe at least linear regression is something that you guys are used to, right? And I think it offers to us like a very nice transition step between what supported vector machine does and what neural networks do, okay? So like, I think that would be nice if we manage to at least learn some concepts in algorithm that's probably is like closer to you guys. So like, let's start with linear regression, okay? So just to summarize, the way how you have this problem usually set up, right, is that we have some input, which is like, we're going to call the X, right? So like by X being in the input, I'm saying that it belongs to the space Rn. So if you remember, N here corresponds to the number of features that I have in the data. Great, yeah. And the features usually corresponds to how many columns I have in this data, right? So like in this case, I'll have n columns. Perfect, yeah. So in the linear regression, if you recall, right, what we do is essentially the multiplication of the features of this data. So that would be an x1, right? X1 has n features, so that's feature 1, 2, 3, 4, all the way to n, right? And what we do is to multiply that with a weight vector that also has n elements to it. And what we are trying to learn is like, what's the value that I should have for each one of these weights in W, right? That are going to assign a degree of importance to these features that are coming from X, right? And give to me estimator Y hat in this case. Okay, good so far, right? Now, if you want to combine that in the framework that we have been using so far, which is that like, okay, now I have to find a way to combine this information that's coming from the input. So remember that here, X corresponds to the input, right? To the information that's coming from the output, Y, right? I have to somehow find a way to compare what's the output of my model, which is f of x, to the ground truth, and then use the appropriate metric. Like we have seen a couple of metrics. So for example, I can compute the R square between the two, or I can compute what's the error and so on, right? And that's how I'm going to evaluate how well these weights that I have trained, they approximate the true values. Okay, so that's the general framework of the problem here. So let me delete all this stuff. Very well. So if you guys remember, we had defined the learning algorithms as being a task, right? Where the task could be anything, including a linear regression, a regression problem. Then the next thing that we had to do was define learning experience E, right? Since we're doing a regression, that's supervised learning. It's so hard to write with this thing. I'm glad that I'm repeating it out loud so you guys can remember what I'm trying to do. And P is the metric, right? That we're going to be using. What is the metric that we use for linear regression? When you're trying to fit linear regression to data, what's the metric that you use? Okay, yeah, for the sake of time, the metric that you use is the mean square error, right? So again, now we have what's the ground truth, right? Which is like the data that's coming from the true values, the Y test, right? Remember that we did that for the supporter vector machine tutorial, right? We had a full table, X, right? We selected the first 20,000 rows from it. And then from that, we split this data into a X train and a X test, where these correspond to 0.75 fraction of the data, and this was 0.25. Okay, so that's the Y test here, essentially, right? During training, of course, we use the train, right? So you can replace this with like Y hat train, which would imply the output of the model, right? This estimation of the model combined with the weights. For the train data. Okay, so what we do is to compare the output of our model with the ground truth data, okay, and see how far off we are. And then we need to update these weights, right? Because like, okay, now I know how bad is my output, right? I have to do something with respect to the way how I'm taking in this information. And the only thing that I can manipulate in this case is what the set of weights that I'm using to evaluate the importance of each one of these features that I'm taking from the data. Okay? And that's essentially like the updating process of like how we train linear regression. So let me delete this stuff again. So once again, this is the formulation of how you train the method, right? So like you make a prediction based on the set of weights that you have chosen for the current training step. You multiply that with the features that are coming from your data, right? Now you have a prediction, right? Which here would be the Y hat for train. Okay. Now I compare that to the ground truth information, which is Y train, right? This is the formulation of the mean square error. So like I compute what's the difference between what was my prediction and what was the ground truth, and I take the square of that. What's the benefit of doing that? Is that things that are further off, right? They're gonna have like higher importance, like for the error, right? So for example, if these guys, they were like the difference between the model output, which is W times X, was 2, for example, right? This is gonna matter with importance of 4. But if this difference here was actually 8, now this comes to the overall loss as being 64. So like I'm gonna penalize higher for like the outliers, right? This can be a good thing if you are trying to like make good predictions for outliers as well, right? But if the outlier is actually just like noise, then it can become problematic, right? But luckily we know that there are some other methods that try to account for that. So for example, we now have seen that support vector regression in the classification, they have that C parameter that says like, I'm willing to give this much of like error for the outliers, and that's still okay, okay? Now, anyone here can tell me what is this symbol that we're putting in front of this MSE loss? So again, this that we have here, right? This is nothing else than the MSE loss. So like that's how we compute the error that this method is doing, right? Now, what this symbol here refers to, can anyone tell me?
It's delta, like gradient, like something like this.
Yeah, it is the gradient. It's just not delta, right? Because the delta would be like this, right? But
sorry,
yeah. No, but it's good. It does represent the gradients, right? So like you're absolutely correct. So what this gradient here implies, this gradient with respect to W, could you tell me?
Is it like finding a minimum or maximum?
Very good, very good. Yeah, so like when you're talking about changing these weights, I need to find a strategy to do this change, right? So for example, I can empirically change the weight, right? let's say that like from this set of weights, I had like any weights, right? You see that I have weights going from W equal to 1 all the way to W equal to N. I'm gonna get just the first one, and I'm gonna make this plot where basically I change a little bit W1, right? And I inspect how much of an impact it had on the mean square error that I'm getting, okay? So let's say that I started here, right? Like with W equal to 1, I see that I had this much error. I change a little bit. Oh, I'm going down. Yeah, let me keep increasing this, right? Until you finally start seeing that this thing is going up, right? So you see that this was a process that, although manual, it basically entails like every time that I make a change W, right? I would like to know how much I'm affecting the loss. So this is what the derivative does for you, right? So like every time that I make a small change to W, I want to see how that's going to impact in the loss. Now we start talking a bit about like calculus here, right? Because for example, if I want to find what's the part that's going to give me, what's the W that's going to give me the lowest loss that I can, I'm looking for this point here. Can you guys think of any technique or approach that we can use to find this point that's going to minimize this loss for me for any given W? Anyone?
Like the derivative.
Take the derivative. And there is something very special about this point, right? With respect to the derivative. What's special about that point?
Zero derivative.
Is zero derivative. Very well. Yeah. So like you see that like this partial derivative that you have here, right? So for those that are not like familiarized with this symbol, what's the difference between this symbol and what I just did down here, which is just the derivative of the loss with respect to the weight? Can anyone tell me?
So all dimensions, every dimensions in the W.
Perfect. Yeah, exactly. That's the case. So like this entails that I'm going to take the derivative of this function with respect. So let's say that this is L, right? Derivative of the L with respect to W1, derivative of L with respect to W2, and so on, right? Because here I have done this inspection just for W equal to 1, right? But in fact, I want to optimize all these W's that compose the weight vector. Okay, is that sort of clear to everyone? Any questions with respect to that? Okay, and this works pretty well, right? Like linear regression is it's a very simple method, like quite elegant, if you ask me, you know, but it has its limitations, right? Essentially, is there anyone asking anything? Okay, yeah, I thought that maybe our voice is in my head. So there are these set of problems that linear regression can handle, right? Which essentially they are in the family of like linear problems, just as the ones that we have been discussing so far, right? So like we're just gonna feed, you have some data, right? That's conditioned a specific variable of interest. And if this is a linear problem, you can feed a linear regressor, no problem, and it's gonna do great. But then it fails when you're talking about problems that are more complicated, right? And we're gonna see some of them. I'm not gonna spend too much time motivating this right now, but like we're gonna see where it breaks. Very well. So now with respect to like doing this minimization in higher dimensional space, right? We have been talking about doing that minimization with respect to W1, right? But in fact, when you start taking this problem, which like is now composed by the loss, right? So like disregard the fact that it's C, but you can imagine that this is loss, right? So every time that I make a small modification in let me change this to W1 and W2 and all the others, right? Like here we're just plotting the first 2 dimensions of this vector. We're going to observe that we're going to be moving around this landscape that now is describing the loss, right? So that's why we're taking the derivative, because like now we're in just the derivative, but rather the nabla, right? Which is like the partial derivatives of the problem, because we're trying to minimize these laws with respect to all these weights simultaneously. Okay. Any questions with respect to that? And then like as we just saw, right? This point where we have the lowest loss, luckily it's defined by this very cool characteristic, is that ideally when I get to this point, right, the partial derivative with respect to all the weights that I have is going to be equal to 0, right? So I have this very clear the optimization technique now, which like evaluating how much I change my weight, right? And how that impacts on my loss, right? But like, I'm not trying to minimize just the loss, but like, I'm trying to find the point where this derivative is equal to 0. So like, yeah, I have like a very clear technique in a way how I can change the weight and inspect in real time if I'm going the right direction or not. Okay? Any questions? So this is just the formulation of what we just described, right? Which I'm going to skip for the sake of time, but that's essentially the same problem. So like here we have the weights that we're trying to train. This is the input data, right? This is the summation over all the samples that I have. So like I compute the error for all the samples that I have in my data set, right? Because we have been discussing about like just a one single sample, but you accumulate this square error over all the samples that you have, right? And what you're trying to find is the set of weights that, given the data and the weights, I get to minimize my loss, right? And I do that using gradients, the computation of the gradient of the loss with respect to the weights. All right, that's in very high level, but if you have any questions, I can point you towards more resources. So I'm going to skip this. Okay, so little exercise here. So we have been talking about these points that have the derivative equal to 0, and that's what we're trying to achieve, right? So can you point to me the points where I would have the derivative equal to 0 in this plot? Perhaps I even have a quiz where you guys can answer that. And then I can turn it on and let you guys vote on that. I think it's this one. So I'm gonna activate this. Perfect, yeah. So please vote in the points where I have the derivative equal to 0 along this curve. And then we're gonna discuss. Wow, a lot of response. Oh, yeah, because it's multiple answer, yeah. You had to vote in more than one. That's why. Okay, 31. So I guess we kind of got to a stable point. All right, let's see. So most people recognize D as being a point equal to 0. A lot of people recognize H as being a point equal to 0. Okay, I got several B's, F's, and K. Very interesting. Okay, so let's discuss that. Okay, so the people who voted for D and H being equal to 0, you're correct. Now I see that a lot of people are kind of like on the wall with respect to like B and F. You guys who voted for B and F, can you explain why you voted for B and F?
Because the derivative equals 0 for the minima as well as for the maxima of any function.
Exactly. Yeah. So you're completely right. Let's go back to this slide here. So in this slide, all I asked you for is the derivative equal to 0, right? So like the derivative equal to 0, we have seen so far this guy and this guy, but they are equal to 0. They are local minimas, right? But the local maxima here is also equal to 0, right? So like, in fact, now I have to be very careful when I'm trying to optimize the method, and just keep in mind that what I'm looking for is the derivative with respect to the weight being equal to 0, because that can take me to where I want to go, which is D or H, right? Like potentially is like, what's the global minima? So let's say that this one takes me like to 0.1, this one takes me like to 0.09, right? So like in this case, what I'm looking for is the global minima, which like in this case would be H, but they are minimas in this problem, right? And what are these guys? If these guys are local minimas, these guys are local maximas of this problem that I just presented to you, right? But both satisfy these requirements. So we need to put extra constraints with respect to like, okay, I'm looking for the derivative being equal to 0 when I'm trying to minimize the loss, but I is not anywhere where the derivative is equal to 0. Like it has to have more constraints, and we're gonna see where these constraints come in. Okay, with respect to like the derivative being equal to 0 in B, D, F, and H. I think that's clear to everyone. But there is one more thing that we need to address. You see that a lot of people voted for K as also having the derivative equal to 0. Can anyone who voted for K comment on that?
I voted for K, but actually now when I see it, there is a discontinuity, so then derivative cannot be derived on discontinuity point. So could be a trick question, yeah, and a false answer.
Yeah. No, you're completely right. Yeah. So what's the problem, right? You said that there is a discontinuity, right? So like, what's the problem with this discontinuity? Is that the derivative is poorly defined, right? If you remember, what's the definition of the derivative? It can only be touching the curve in one single point, right? And it has to be unique as well. So like, when I try to do that for this point here, I can't touch these points with a single curve, right? The problem is that this curve is not unique. I have several curves that only touch the point once, right? Which doesn't happen for all the other points. But like in this one, because it has like a little elbow here, I have several curves. So like the derivative here is poorly defined. Okay, so like this point here is poorly defined, therefore the derivative is not defined there. So like it cannot be considered as a region of minima. Is that clear for everyone? So like I'm touching these ideas without getting too much into the math of it, but if you need a refresher of calculus, please let me know and I can point you towards more clear resource. Very well. So another very important thing with respect to the process of optimizing, and we also saw that while we were studying the supported vector machine, is that you want to penalize also the weights, right? So it's not any weights that you're looking for, but you're looking for the weights that they try to minimize the magnitude of the weights, right? So like you're trying to minimize the loss, which we have seen several times, right? So like you have the loss there, and you're trying to change the weights in order to get closer and closer to the global minimum. Whatever, yeah. Remember that I said global minimum, right? But also, it was the same thing with supported vector regressor, right? We also had that term that was the magnitude of the weights, right? And back then, I said, without getting too much details, that this was a regularization technique, right? And we discussed why that was the case, because if I have one weight in this vector that's just much bigger than everything else, so like we had 0.1, 0.2, and then I had like 1000 here, right? These might facilitate that I achieve like some degree of overfitting, because then that means that I'm giving way too much weight to one specific feature of the data, right? And I don't want that, because if I give way too much weight for that feature, when that feature changes a little bit, I change a lot my prediction, and that's not good, right? Therefore, we want to put some regularization with respect to these weights, right? And the way how you regularize for these weights is basically what tells you about from the different types of regressions, right? So for example, other methods that are quite popular, right, is the ridge regression, which probably you guys have heard of, right? The loss component is exactly the same as we have discussed so far, right? So like is this combination of like model output with respect to ground truth. And then I have this L2 penalization for the magnitude of the weights, right? Which, if you guys remember, that was exactly the same thing that you had for supported vector regression. So I hope you can appreciate where these things start to overlap here, right? The difference between these and the lasso regression, which is also a very popular regression technique, is essentially that here I'm not taking the square of the weights, but rather just the absolute value of the weights, right? So here I have just a L1 norm normalization. So like here I penalize the bigger weights with higher penalization, and here like that's a little bit less strong. Okay, good. Any questions with respect to that? So here would be the cartoon diagram for that, right? So besides all this, did someone have a question? Yeah, please.
Yeah, I have a question. So what happened if it's really the case, you know, that we have 10 features and it's only one that is super related to the what we were predicting. So it's really that this weight should be higher than the others. And now we are doing regularization. So then it's probably a mistake, or yeah.
No, but look, that's like their regularization is going to be penalized, and these weights, they're going to be decreased if that helps overall the method, right? Because I'm not trying to minimize just the weights, but I'm trying to minimize also the loss, right? So like these losses, let's go back to this slide. These losses, they're composed by two elements, right? Which the first element is how much the loss is changing with respect to these weights, right? And the magnitude. So I'm not minimizing just the magnitude. If penalizing the weights actually decreases the performance of the method, then these weights, they're going to keep fighting to be higher, you see? So like you have both components that need to be optimized simultaneously. All right?
Yes, yeah, thank you.
Mm-hmm.
Yes, and if possible, one small question. You mentioned the analogy between this regularization and support vector machines method. So what is exactly the analog the analogous parameter to these weights in case of support vector machines? So if I understood correctly, it's a C parameter, or maybe no, not so.
No, the parallel that I was trying to make here is with respect to the type of penalization that we do to the weights, right? So like if you come all the way back here, someone asked me in the first class why we were penalizing the norm of the weights.
Okay,
right?
okay, I understood now. Thank you.
Yeah. Good. Very well. So like this property that I'm talking about like not assigning too much weight, like for one specific feature, right? Like people call it the preference of the model of sharing like smaller weights. And that essentially puts you in this case, right? So like you try to give as much as you can the same importance that you have to all the features that are part of your data, right? Because you don't want to be in this case where like one feature is completely disregarded, right? Simply because I can try to, I can make a good prediction using just one feature, right? Most often, let's think about some other case. most often I have like linear dependence between the features in the data, right? So let's think of some. For example, if my data was coordinates of where I collected the data, right? So like, so the X and Y, and then the next one would be like precipitation, right? So for example, if this X and Y corresponds to the Amazon forest area, right? Precipitation is going to be highly correlated with those features already, right? So like you don't necessarily need all of them. So like, if I had the coordinates of like the rainforest, like the rain is almost a given, right? The amount of rain that I'm going to get there. So like you could find a model that if it's not properly regularized, is going to start paying attention to just precipitation, not like the location of where that sample was collected, right? But you don't want that because like then you're susceptible. Let's say that for some reason, the precipitation information was corrupted, right? And now because I don't have precipitation, I just have a model that's not capable of predicting whatever I was trying to predict, right? But like if I have some redundancy, so if I enforce the model to use as much as it can, like all the information that I'm presenting, I have a more robust method. Okay, does it make sense to everyone? But there is another benefit of doing that, which is that I force the problem to be convex. Okay, and what does it mean? When I have the weights sort of being regularized, I get closer to this case. This is a convex problem. In a convex problem, it's easier to solve because like when the problem is convex enough, I minimize the chance that I'm going to get stuck in areas that are like just local minimums, which is undesirable, right? In the reality, let me go back to full screen. The reality is that most often, like problems that you're going to find in the wild, they usually correspond to something that rather looks like this. It's like very irregular, the loss landscape that you're trying to minimize. So like you have a lot of chance of getting stuck like in some spurious local minimums like here, or even like some local maximus, right? So like you're looking for this sweet spot here, which is like the basis of this loss function. If you don't regularize, you increase the likelihood of higher occurrence of local minimums, right? And that's like when the problem becomes highly non-convex, right? If you regularize, there is quite a bit of theoretical work on that. You move away from this and get closer to this. Of course, not as smooth as this. Like this doesn't really happen like in nature, right? But like you, at least you get a little closer to getting something that's smoother and therefore easier to train and regularize and like feed to the data. Okay. Questions? It's 1:40, right? Okay. Questions? I think someone put something in the chat. I haven't done any calculus in a long time. Okay. Cool. Yeah, I'm gonna send some extra material there. For the sake of time, probably I stop here, right? Before I start like perception then. And then I leave this rest of the class for questions.
Yes, it's fine.
Okay, yeah, so we have another 5 minutes, I think, right? So like any questions with respect to what we discussed so far? So look, let's recap, right? Like what we have done so far. So we had discussed like supported vector machine, like in details, right? We saw that being applied for both classification and regression. And then we saw that like, okay, so the regression problem can be characterized essentially as being little tweaks in the weights that I assign to each one of the features, right? And how I optimize the weights, I change the weights by inspecting by how much I change the loss every time that I change a little bit, each one of the weights that are composing this hyperplan that essentially stands for like the position of this regressor hyperplan, right? I hope you can appreciate at this point that these weights, they're basically just defining the position in space of a hyperplan, okay? So like every time that you're talking about the weights of a model, think of a hyperplan that's trying to either be fit to the data, right? In the case of a regression, or trying to separate data sets or classes in the case of like a classification problem, right? But the hyperplan is I hope it's a concept that you guys are gonna take from now on every time that you're talking about like changing weights of a model. It's always like in terms of a hyperplane. Okay, and these weights essentially they stand for like what's the position of this hyperplane with respect to the data. Okay, and then we saw how that was being applied to support a vector machine. We saw that like in a case that's closer to you guys, like many of you said that you already have used linear regression before, so we just had like a review on that, and now we're going to see how we use the same concepts to train the perceptron, which is like these small units that compose these large neuronal networks that are now considered the state of the art with respect to like machine learning. Okay. We still have 1 minute. Any questions? So what I'm gonna do? Yeah, I'm gonna send you guys, like, I'm gonna reply to that email that Pepe sent to you this morning, today actually, and I'm gonna send some extra reading material there, and then you feel free to like review that material. So it's gonna be like a review on linear algebra and calculus, right? Which is gonna give like a even deeper refresher on the things that we talked about. So like the product of vectors, we discussed derivatives, so like you're gonna have all this information there, right? And because we're just gonna keep building on these concepts that we have discussed so far. So like this is gonna become like even more important from now on when you start getting closer and closer to like playing with actual like neuronal networks. So it's important that you guys have these concepts like fresh in your mind. Okay. I guess that's it for today then.
May I ask a small question? Is if I have a data set and I just use the supported vector machine, that simple model for like tree height, then is that strictly sense? Is that like a machine learning calculation?
Yeah.
That's
Absolutely, yeah.
that is the concept behind that one is kind of like a multivariable stats, right? It's
Yeah. Everything that you're going to be doing from now on is multivariable analysis. Yeah.
Okay.
Mhm.
So what
We're
I'm
talking
just
about
wondering, what is the difference between the classical multivariable stats and the supported vector machine? Is that it eliminates some of the outliers, right? Is it
what do you call the classical? I would say that supported vector machine is quite classical.
Yeah,
Yeah,
Giuseppe, you know some of the paper in the past like 20 years, the ecology is like just
okay.
Kind of
Whenever you do, and maybe Antonio, correct me if I'm wrong. Whenever you calculate, I mean, use the multiple regression analysis, multivariate regression analysis, you find only one coefficient for one particular variable. Correct, and that one is nothing else than the coefficient that multiply the temperature, another coefficient that multiply the precipitation, and so on. Okay, rather in the machine learning environment, you don't have one coefficient for that variable, but you have multiple, isn't it, Antonio?
I mean, you can think of these weights as being independent coefficients that are multiplying
the weights are nothing else than the coefficient, and they are not only one, there are many. So you don't multiply the variable for only one coefficient, but you multiply the weight. You multiply in one section, you will have one weight. In another section of the data set, you will have another weight, and so on. That's why you have.
It's the same weight. It should be the same weight.
Is the same weight?
Yeah, it's the same weight. Yeah. So like that's why I'm trying to understand what you were calling the classic.
I'm like
multivariable stats. Yeah.
Like maybe Giuseppe, you're very familiar with like or maybe 20 years ago the forestry or the ecology is like we just maybe like a tree height equals a coefficient times a precipitation, and
Yeah,
another
but
coefficient.
you remember that, let me share this.
That's the same, right? That's the Antonio. You mean that's the same concept?
Yeah, it's the same concept. So like
Yeah.
machine learning didn't invent the wheel, like all these things, they are just being inherited from like classic statistics, right? So for example, okay, just to address the first comment, right, which was with respect to like you had these variables which are defined as like the features of your data, right? So this is a sample. And what you're trying to find is this weight vector, right? Which has these values, blah, blah, blah. These can be considered your coefficients, which are, these here would be like the position, precipitation, right? So elevation, right? Those are the coefficients that we're multiplying, because remember that like what the model output stands for is the product of W and X. So those are the coefficients. So like, machine learning didn't invent this. This is coming from multivariable data analysis.
Yeah, but is it one for that particular, is always the same for that particular temperature, for example?
No, this is general. This is a model, right?
Yeah.
So,
okay, get it. But for the full range is only one weight.
what do you mean range?
Okay, the range, the temperature goes from -50 to +50. So you have one weight for the full range of temperature.
So, okay, maybe now I understand what you're trying to say. So like, these, what I'm describing here, it's like for regression problems, simple regression problems. Now what you're describing there is like zoning of the data, right? Like where the model is supposed to change its function, right? Everything that we have discussed so far, remember that it has been for linear cases, right? So now we're going to move like towards more complicated case. Remember that I said, okay, linear regression works great for when the problem is linear, right? So like everything that this classic multivariable analysis that we have discussed so far works great for when the problem is relatively simple. So like, oh, what's the coefficient that I should use to multiply elevation? Then I have a different coefficient that I should use to multiply precipitation, like in order for me to predict the height of the tree, right? But like, of course, then as the problem starts becoming more and more complicated, right? Now you have to change the rules slightly for different areas of the data, right? Which is a thing that we haven't discussed yet. So like, then it becomes more complicated. Neural networks, they're going to do that for you, but not to support a vector machine.
Thank you.
Yes, and in the case the variables are interrelated between each other. For example, there is often the case that the one variable could modify the impact of other variables. So could support vector machines, for example, to treat well such cases?
The case where one feature impacts on the value of the other feature?
I mean, when the predictor break the rules of autocorrelation between the predictors, So one of
breaks
the assumptions,
rule of autocorrelation. Which rule is that?
one of the rules inside to the multivariable analysis in the classical statistic is that the variable should not be correlated. I mean, the predictors.
Oh, ideally,
should not be correlated.
I see,
among themselves. So if you have, for example, in our case, temperature and temperature and elevation are strongly correlated, and you should take it out one of the two. So
you remember when I'm
so Alex was asking, is also this one rules that we should take into account for support vector machine?
We don't have to, right? Because remember that even if you have two variables that are correlated, right, you could simply just like pay attention to one of them, right? The machine could simply start paying attention to one of them by assigning weight 0 to one of these variables. But you don't want that, right? Because like, although they are correlated, one of them might get corrupted at some point. So like we force the method to pay attention equally to both of them in this case, right? So like we don't need to do this manually by simply saying, oh, you know what? Instead of letting the method learn that it should discard that variable, let me discard it by myself. So like I go in the table and I actually remove that predictor, right? So like supported vector machine, because it has a penalty on the weights, right? It tries to force all the features to be equally paid attention to. And that's the characteristics of supported vector machine and the characteristics of neuronal networks. So like if there is such correlation, the method is going to be able to compensate for that.
Yeah. And this is also inside to the random forest. They don't, yeah, they can deal with the autocorrelation of variable, different range, categorical and continuous variables as both as a predictors. So these are the beauty of the machine learning framework in general. Okay. Yeah.
Yes, and also one small question regarding this two methods of regularizations like lasso and ridge regression. So what are the pros and cons of each of these two methods? So what is the difference between them? Maybe not mathematically, but conceptually, like when we use these methods for some predictions.
Yeah, so there are a couple of things, right? Like without getting too much detail. So like the actual formal explanation of the difference between them, you can find here, right? So like I'm saying that like, for example, lasso regression doesn't have a closed form solution, which implies that something that looks like this is just the absolute value. I'm not guaranteed to find a minima, you know? So like this implies like in the convexity of the problem. So for example, the L2 norm, which is what the ridge regression uses, right? So you see that there is a square of the weights there. The L2 norm puts you like in a more convex scenario like this, right? And remember that I said that this is better for optimization because then you increase your likelihood of finding like an optimal solution, right? So the benefit is at least with respect to getting your problem closer to ensuring that you're going to find the optimal solution or not. But then you have other issues associated to it, right? So for example, this implies like in higher complexity of the problem, right? Because now you have to compute the square of the weights, right? So like depending on like how much computational resource you have, maybe you're not able to afford that, right? Or maybe you don't want to maybe that's more complicated calculation to be done, right? When you have like really high dimensional vectors and a lot of them. So pros and cons with respect to computational resource, but getting like something that also makes the optimization problem easier. So those are a few things that you could consider.
Okay.
Okay. Cool, guys.
Okay,
So,
thanks, Antonio, for the deep of this other lecture. So we will resume the lecture and we will meet next week. Please also watch again the video recording if something is not clear and all the material that Antonio is going to send you both to all of you guys.
Yeah.
Okay.
And try to do the exercise, the supported vector regression, like play with the parameters that we discussed today, like see if there is something that like gets you a better performance, like if you get something better than what I have shared with you guys today, let us know. So then we can all learn from this data and from your experience.
Okay. Thank you very much.
Okay.
Bye-bye. Thanks.
Thank you.
Thank you.
Thank you.
Bye.
Bye.